Hey, physical science. Hey, last week we talked about ionic bonding and how to write chemical formulas for ionic compounds. This week I'm going to give a tutorial on how to work with covalent bonds, which are a little different, and how to draw things called Lewis structures. So to start, let me switch over my screen and let's get going. So um, I want to start with neon. Okay, neon is a noble gas. It's in group 8A. So it's on the far side of the periodic table. Okay, and it has 10 protons and 10 electrons. So the protons are in the nucleus, so they'd be in the center of the atom. And imagine this Ne is the nucleus. And then these rings that I'm drawing, those are called energy levels. And the electrons exist in these energy levels. So it turns out neon's first energy level holds 2 electrons, okay, and the other electrons out of the 10 fall in the outer ring. 4, 5, 6, 7, 8. So there's 8 dots around neon. Okay, well, it turns out this is called, the outer shell is called the valence shell, and the valence shell for neon has a full octet. So neon is very stable. Okay, now if I said go to another noble gas, like a much larger one, like xenon, which has 54 protons and 54 electrons, and I said draw in all the electrons around xenon, you'd be putting 54 dots, which would take forever. So a guy named Gilbert Lewis came up with a way to use some shorthand notation where he only drew the valence electrons. So it turns out xenon, which has 54 electrons, still only has 8 valence electrons. So neon and xenon both have outer shells that look similar. They're completely full with their octet and they're both very stable. So even though xenon is much, much larger and has many more rings of electrons or orbitals of electrons, it still behaves the same as neon. Okay, and so Lewis structures can be used to draw compounds, draw atoms, and predict some things about them, like their stability and what they'll bond to. So before I move into covalent bonds, and I keep saying that word, and we'll talk about what it means, I want to review ionic bonds. So ionic bonds happen when there is a transfer of electrons. Okay, an ionic bond, the example we gave to start with was sodium and chlorine. So I'm going to draw their Lewis structures. This might make a little more sense now. Sodium is in group 1A. Okay, even though it has 11 electrons, its last electron in its valence shell, there's only 1 electron. Okay, so anything in that first column, which would be this column, has only 1 valence electron. Chlorine, on the other hand, chlorine on the other hand has 7 valence electrons. 1, 2, 3, 4, 5, 6, 7. Okay, and you'll notice it's one short of a full octet. So its outermost electrons they're kind of like uneasy right now because they're really seeking out an additional electron. So if sodium and chlorine are hanging out nearby, then what happens is sodium, wanting to get rid of its outermost electron, will just give it to chlorine. You guys got to remember, sodium has 11 electrons, 2 in the first ring, 8 in the second, and 1 in the third. So if it can get rid of that 1 electron, its inner ring has 8 electrons, which is a full octet. So imagine it gives its electron. I'm going to draw it as a dot. I'll keep it red so that you remember. Well, sodium now being 1 electron short is positively charged. Chlorine, having 1 extra electron, is now negatively charged, and we call that chloride. And because these things have opposite charges, these ions have opposite charges, they're attracted to each other. So those sodium and chloride ions kind of clump together, and you'll get a bunch of them clumping together. For every sodium ion, you get a chloride ion, and they form a lattice or a crystal, which is what Mr. Coffin was showing when he made his salty strings. Those salt, well, basically the ionic bonds held the little pop tab up from falling even when the string was burnt. Okay, and that was basically due to that attractive force. Okay, um, now shifting to covalent bonds. Okay, covalent bonds are the sharing of electrons, and you'll see what I mean here. And we'll talk about the other chemical that Mr. England was bringing up. He brought up chlorine gas, which was kind of that yellow gas used in trench warfare. So chlorine gas, its chemical formula is Cl2. It's made up of two atoms of chlorine. So I'm going to draw the two atoms of chlorine. They're going to look really similar to the starting chlorine up above. 1, 2, 3, 4, 5, 6, 7. I should probably draw it like this. 1, 2, 3, 4, 5, 6, 7. Okay, and you'll notice each chlorine is one short. Okay, well, the problem, if this one on the left tries to give its electron to the right, you end up with one chlorine having a full octet, the other one farther away from having a full octet. And it's not possible to just move electrons. So what has to happen is these two electrons get shared between both chlorines. So to draw that, imagine I cram the chlorines a little closer to each other. And those two in the middle sometimes spend time around there, and they sometimes spend time around here. Okay, and when you look at it together, there are 2, 4, 6, 8 electrons around the chlorine on the left, and there are 2, 4, 6, 8 electrons around the chlorine on the right. So both of them can have full octets if they share electrons. So the Lewis structure for chlorine, for chlorine gas, chemists, instead of drawing dots, when there's a bond, they draw a line, and then they'll put in the rest of the outer electrons. And every time they draw them in sets of two, those are called lone pair electrons, and these are called covalent bonding electrons. Oops, covalent bond. Okay, so the Lewis structure includes one covalent bond. I'm going to do another example. This is another gas. This is a better gas to breathe. Don't breathe chlorine gas, but breathe lots of this stuff. So oxygen gas has two O's, two oxygens, and if you look, they're both in group 6. So I can take their group numbers, group 6A plus group 6A. I need to draw in a total of 12 valence electrons around the two oxygens. So I put O's next to each other, and I draw in 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And you'll notice both of them are too short of a full octet. So instead of being one short, they're two short. So maybe you guys can see what's got to happen. These two electrons have to be shared, and these two electrons have to be shared. And a chemist would draw it more like this. Okay, where there are two covalent bonds between the oxygens. This is referred to as a double bond. And a double bond is going to be slightly stronger, right? Or maybe almost twice as strong as a single bond. It does depend on the atoms that are bonding for the bond strength, but it's going to be a little bit shorter of a bond because you've got more electrons between, kind of holding things together. So it's like adding more glue to something. Okay, and it's also going to be harder to break apart then. So you can predict properties about compounds based on their Lewis structure, and we know chemists have confirmed that oxygen will bond to itself in a double bond. Okay, I'm going to kind of rattle through some more examples. I'm about 8 minutes in, so I've got about 10 minutes left. So stick with me. Let me start out with another compound. Actually, since we're talking gases, we're going to just stick with diatomic gases. We're going to do hydrogen. Hydrogen is in group 1, so I have two of them. 1 plus 1 is 2. I only have 2 electrons to work with, so I stick my 2 hydrogens together, and you can cut to the chase here. They have to share those 2 electrons to make a molecule. So that is a single bond, and hydrogen is weird. It's such a small atom that because it can't accommodate any more electrons, it only needs 2 to be happy. Most everything else needs 8 electrons around them to be happy, but hydrogen only needs 2. So hydrogen, right, this was a very light gas, has a single bond in it, and it's very reactive, and this is what the Hindenburg was filled with. It's really light, so it was good and buoyant. Okay, however, it also is very flammable. So that was what happened when it caught on fire. Let's move into something that has more than two atoms. We're going to say H2O. So water. So water, similar to hydrogen, it's got two hydrogens, but it also has a group 6 oxygen. So 1 plus 1 plus 6 is 8. Okay? And once you've added up the valence electrons, when you're drawing the Lewis structure, the next thing is to put the atoms where you think they're going to go. Now, hydrogen has, or water has 3. So you could do something like this. You could do something like this. And actually, you could do something like this. But hey, those three atoms on the bottom are similar to their ones on the top. They've just been switched. So I'm going to get rid of that one. Okay, then looking at the next two, it turns out water and most things in nature will try to be as symmetric as possible. So out of these two, water prefers and will only bond in that configuration. So it turns out hydrogen, because it can only hold two electrons, you can't hook a hydrogen in the middle of a molecule because it has too many electrons around it there. So I'm gonna get rid of that one, and we're gonna take the middle HOH, and we're gonna try and hook those together with 8 electrons. So what I like to do, I like to just hook them together with single bonds. So that's 4 electrons, 2 in each bond. And then I look and I need to come up with a total of 8. So where can I squeeze some more electrons? Well, the oxygen needs 2 more above it, 2 more below it, for a total of 8. Again, to count them up, 2, 4, 6, 8. That water is happy. Okay, the water molecule has a satisfied octet around the oxygen, and it has 2 electrons around each hydrogen. That is a covalently bound water molecule. Okay, moving on to another one. I'm sticking with the common ones here. You guys should recognize this one. This one is related to Mr. England's experiment. He's going to be doing hopefully some Diet Coke and Mentos experiments with you guys. So carbon dioxide is what makes pop fizzy. It's what we're concerned about climate change, and because we're pumping a lot of CO2 into the air since the Industrial Revolution. And so CO2, what does its molecule look like? That's where we need to draw a Lewis structure. So if we look at this one, carbon is a group 4A element, and you have 2 oxygens, both group 6. So I add them up. I have a total of 16 valence electrons. Now to make CO2 symmetric, the carbon has to go in the middle, and the 2 oxygens will go on the outside. Okay, and here's again my process. I start adding electrons, 2, 4, I hook them all together, 6, 8, 10, 12, 14, 16, and I've used up 16 electrons, and you're thinking that looks pretty good. However, there's a problem. Right now the carbon, if you look around, it has only 2 bonds, which counts for 4 electrons, which means carbon doesn't have a full octet yet, but it wants to. So this is kind of cool. You can erase or cross out lone pairs. What I'm doing here is I'm forming new bonds. So I've crossed out 2 lone pairs and formed 2 new bonds. And now, if you count them, I still have 16 electrons. So I've got 2, 4, 6, 8, 10, 12, 14, 16. However, around the carbon, you can circle them if it helps. There are 8 in there. There are 8 in there. And there are 8 in there. So carbon dioxide ends up, its Lewis structure ends up looking like that. Sorry, these dots were bad. Okay, so carbon dioxide looks a little different than water. It's got more electrons around it. And chemists can look at this and they can predict shapes, but that's a little beyond where we're going. But turns out carbon dioxide is a linear molecule. Water does some funny things because of these lone pairs in the middle. Water ends up being a little bent or angular molecule, and carbon dioxide ends up being linear. Okay, so I'm going to do one more example, and then I'll explain how you're going to try your homework. And if I'm going too fast, you can always go onto YouTube. You can type how to draw a Lewis structure for, and it will give examples. You can type in whatever chemical you want to draw a Lewis structure for. But what's really good is to watch how other chemists and how other students are drawing these structures, because you can always look them up. Okay, you can look up what these chemicals and what the compounds look like and what their Lewis structures are like. However, it's better to learn about the process, and then you can apply it to many other chemicals. So it does take practice. I'm going to draw the last one. And if I have some time, I'd love to go do a little video with an acetylene cannon. But I'm going to draw acetylene right now. So acetylene is C2H2. So 2 carbons, 2 hydrogens. So if I'm drawing this, again, 4 plus 4, okay, carbons in group 4, or hydrogens in group 1. So I've got a total of 10 electrons to work with. 4 atoms, 10 electrons, and I know hydrogen can't go in the middle, so I put my 2 carbons in the middle and the 2 hydrogens on the outside. And I start filling things in. Now, one way, just fill everything in so that it's happy. 2, 4, 6, 8, 10, 12, 14. Okay, I've used up 14 electrons, but I only have 10 valence electrons to work with. So how do I reduce the amount of electrons with still keeping things happy and having 8 electrons around it? Turns out I can remove 2 lone pairs and put in a double bond. And now I can count them up. I have 2, 4, 6, 8, 10, 12. I have 12 total electrons, which is still too many. So if you guys can see where I'm going, I can remove those 2 sets and replace it with another bond, making that a triple bond. So if you look around this carbon, and I'm not going to circle them this time, I should have 8 electrons. Can you see all 8? I should have 8 around this carbon. I should have 2 and 2 to make the hydrogens happy. And in total, I have, I think there's 5 lines, 5 covalent bonds, a triple, so a triple and 2 singles, and that should add up to 10 electrons. Okay, so you always check, add up your valence electrons, you try and make all the atoms except for hydrogen happy with a full octet, okay, and you work in groups or in sets of 2 electrons. So again, bonds count for 2, lone pairs, each dot, right? So a lone pair of electrons is 2 electrons or 2 dots, and you need to have 8 electrons around each atom. Okay, so for the homework assignment for this one, I'm going to give you a series of things to draw Lewis structures for. So it'll be similar, probably about 6 to 10 different chemicals. And so if I was to give you hydrochloric acid, which is HCl, so let me zoom out, simulate your assignment. If I was to give you HCl as an assigned problem, then what you're going to have to do this week, instead of doing it in Google Docs, you're going to need a piece of paper. Let me switch to this. You would write out the chemical HCl, okay? And I'm not going to show you the whole process on how I do this, but we've just gone through some examples. You would then draw your answer, okay, down below. So hydrochloric acid ends up looking like this. It's Lewis structure. Everything is happy, okay, with a full octet, and then 2 around the hydrogen. And then I did this a little big, but you could put your next problem here. You could put all your problems on one sheet, put your name at the top of the paper, and what you'll do, take your cell phone, take a picture of your paper, and then once you've got your picture, you can attach it to your assignment. So if you have any problems attaching it, let me know, let Mr. England know, let Mr. Coffin know. We'll help you get it. But this week, part of the assignment at least, you're going to need to attach hand-drawn work. I know you haven't written in a lot of your classes. You've been typing a lot. So practice. You guys, maybe if I haven't mentioned it, I always do my L's in lowercase L's as a loop when I'm talking chemistry, so that you guys can see that it's not an I or a 1. Although when I draw it too squatty, it looks like an E. But that's a little cursive L just to make it look different than an I. Otherwise, it gets confused with iodine a lot. So have fun with the Diet Coke and Mentos. Sorry this went a little long. Have a good week. I'll talk to you guys later.